Good evening to everybody. My name remains Timothy. This night we are continuing from where we stopped. We are still on the training on machine learning with deep learning with Python. Today marks the 8th day of our training sessions. As we begin this night, April 2024, this night I would like to introduce to you our tutor in person of Ayobami Salau. Ayobami, please take charge.
Okay, sir. Okay, good evening, everyone. So we are going to be talking about the assignment that was given to us. So I don't know, out of everyone that is present in the class right now, so I think we have up to 15 people in the class. Yeah. So I don't know how many of us have actually done the assignment. Okay, yeah. Okay, Mrs. Okay. Okay, I think Dr. Kazim is using up his hand. So you can talk, sir.
Yes, sir. I've translated all. Well done, sir.
Yes, sir.
Yes, sir. I've submitted my own. And I think Dr. Timothy said about 6 people submitted also.
So can you in 2 minutes, can you, I don't know if you have it in front of you there, if you can just share your screen just to show us what you conveyed. So we can comment. So I want to make some comments. So I want to see maybe you actually conveyed the idea very well. So we can
Okay. Let me
make some adjustment or contribution.
okay. Let me try to share my screen then. Um,
Just only for 3 to 4 people. So I think that should be okay. So maybe then in the next class we might properly attend to that so we can go into other things. So I just want to address it so it won't be like we are not talking anything about it.
I want to suggest that if you have like one or two people to talk about something, that we can face on today's work. So the solution can be shared with them probably after you discuss it.
Okay, make 2 persons is okay. That's
Two
two.
percent is okay to save our time. Rotarian Ambassador Kazim Olajide
yes,
Makinde,
sir.
can you talk,
Yes, sir.
please?
Yes, sir. I'm sharing my screen
Okay, all right.
so that I can just talk briefly on this. Okay. Can we see my screen?
Okay, I think it's still presenting. Okay, yes. I think yes, sure.
Okay. Yes, good evening, everyone. My name is Makinde Kazim once again. Well, from the question that we were given that we should try to bring up a researchable topic or research idea that is applicable to deep learning. I'm presenting from the field of financial accounting, and I want to use predictive model of deep learning to actually predict the financial performance metrics that will be more suitable in measuring companies' performance. Because I have noticed that in so many journals, so many articles, so many publications, there are so many performance measurement metrics in determining the financial health of companies. But I want to believe that with deep learning can actually give us a more specific performance measure out of the so many performance measures that we have. These are the types of the performance measures we have. I hope you can see my screen. We have profitability ratio, we have a return on assets, we have liquidity ratio, we have current ratio, and about 10 performance metrics. So I believe that with deep learning, when we subject these various types of performance measurement metrics to deep learning, it will give us the most accurate and the one that can predict the real performance of of companies in Nigeria. Specifically, I want to focus on manufacturing companies to determine whether profitability, whether return on asset will be the most appropriate one to measure financial performance of manufacturing firms in Nigeria. So that is just what I have in mind. So thank you, sir. And these are the objectives. Objective one, to develop a deep learning algorithm-based predictive model for financial performance measurement metrics. Then objective two, to evaluate this model. And then after evaluating, I will now compare the results, then to explore the impact of this in decision-making process. So that is just what I have in mind, sir. Thank you, sir.
Okay. Okay, sir. We can okay, before I comment, can is there another person that wants to show us
I think you can
what
comment
you
on it
mentioned?
so that this person can move out of the sharing.
Okay. So what I want to ask is this, so what is the target itself? Because I'm seeing a lot of features here. So what's the target itself?
Yes, like I said before, the target is to actually predict out of these various performance measurements, to predict the most accurate and the most appropriate one that can really say that, okay, oh, liquidity ratio is the most appropriate performance measure in evaluating companies' performance. So using deep learning to predict any of these performance measurement metrics to give us the most accurate one. That is the target, to make to
Okay.
give us accurate one out of these various types of measurement metrics.
Okay, now if I get you well, sir, you are trying, is it okay like profitability? Is it like a profit that is a target or liquidity? And
All
for us to
of
get
them,
the
they are performance measurement metrics. If you want to measure the performance of a company, we can use profitability, we can use profit margin, we can use asset turnover. So
okay,
those are the features. So I am thinking in a way to subject all these features to deep learning to now predict the most accurate out of these about 10 features of performance metrics.
okay, okay, no problem. I think we still have to look into it. So when I have access to what we submitted, so I'll be able to give comment and ask some questions. So I'll just give comments so and I'll convey back to the respective people that actually sent the assignment. So to
Yeah,
clarify some things. Yeah.
I'll communicate that with you.
Okay, sir.
Someone is going to ask question. Dr. Chinedu, want to ask question, please?
Okay, good evening, everyone. Mr. Presenter, thank you for your presentation.
Yes, sir.
The comment I want to make to you is that, I don't know, are you a master's or PhD student?
A PhD.
Hello?
PhD.
Can you hear me?
Student.
Okay, okay.
Yes,
So the
can
thing
hear
is
you.
that, you're writing something or making a presentation, you should know your audience. This audience here are made of people from different backgrounds. We are not
Sure.
accounting professionals. So when you want to make presentation to us, you first of all give us a very brief background so that we actually know. That's why the instructor is asking you what are the features and trying to figure out things. So you give that background so that somebody will understand exactly, and be able to link the question, the research question and problem to machine learning concepts. Then you can now, that is before you now start talking about the solution you're preferring. So that is the problem here, because I don't know what is your, like the features or the variables, or even whatever it is. So what I'm saying is that when you want to make presentation for this kind of audience, try to think about that so that everybody will understand, be at the same level with you. I know you know what you're doing, but we don't understand it because we are not at the same level with you in this area. That's the comment I want to make. Thank you.
Okay, so I think
So, Ajayi,
yes.
comments? Dr. Nuruddin, your comments?
Yes, sir.
Thank you.
Thank you very
Okay.
much. Mr. Presenter, you really try. But I see more of structural equation modeling in this your topic, where we talk about factor loading. But you mentioned n variable that you want to see if it's loading on the particular company. So I see this particular topic and this aim in factor loading, which will always refer to structural equation modeling.
Ye- Hello,
We're with
hello.
you. We're with you.
Yes, sir. Actually, we can use structural equation modeling same for this, but same cannot give us the actual feature we are looking for. Same will only give us the loading, that is the contribution of each of the features on the construct. For instance now, profitability is a feature here. So under profitability, we have return on assets, we have asset turnover, we also have liquidity. These ones are under profitability, that is the component of profitability. So what SEM will do for us, it will only give us the contribution of these constructs, of these features on profitability. But now deep learning will give us the predictive value. How can each of them give us the actual indicator, that is the actual performance of each of these features? It is not that one will be depending on the other like same. I don't know if I answered
Yes,
that question accurately.
I can get it. Mm.
Hello.
Hello, Sam. You know
Hello?
what? This is what we'll do. Like I said, I will go through it and I will give comment.
Okay.
So when the comment reaches your site, SARS, then you can make necessary adjustment and clarifications, and you convey back to us. Then I think that will be fine. So we can move to the next person. So we'll just take one more person, then we'll move into what we want to do.
Do you have another person that want to talk about his assignment? Dr. Chinedu, do you have your assignment with you there?
No, I didn't do it. I complained yesterday that I didn't see it earlier.
Okay, all right. Okay, please, let's
Thank
move
you.
on, please. Let's move on, please, on the next
Okay,
topic.
sir. So we're going to be talking about the deep learning model. So I'll be sharing a portion of my screen. Let's see. I think we can all see my screen now.
Yes,
Yes.
we can see your screen clearly.
Okay.
That is go collab.
Exactly.
All right. Somebody raise hand again. Dr. Chinedu, anything again?
No, I didn't raise that.
Okay, all right.
Okay. So this is what we're going to do today. So we want to talk about the the deep learning and the machine learning code that we were treating yesterday. So, and this is what we're going to do. We're going to try and um, upload the data that we were using yesterday. So, I'm going to upload that. So, we just uploaded the data. So, you can see my screen here. This is the data. So, and now what we're going to do is this. We'll try as much as possible to, first of all, I just want to run us through the uh, okay. Let's go back to this. So we are going to import some libraries. So I want to run us through the linear regression part. So we are importing NumPy, Pandas, Matplotlib, and linear regression from scikit-learn linear model. And then we are also importing train test split from model selection, which is inside scikit-learn, and metrics. We are importing a mean squared error and mean absolute error. So how are we going to try to do? And
Can you
we
please
already run this.
enlarge your screen so that we are
Okay.
able to clearly very well? All
So
right, that's good.
uh, now we have run this line of code. So we have run it and everything is running. So now the next thing we are going to do is we're going to try and load the data from a CSV file. So we'll try and load our data from a CSV file. A CSV file that I've prepared. And to do that, we're going to call our data, we're going to call it data is equals to that is pd dot read underscore CSV. Then yes, so and we are going to now put the name of that data. So now the name of the data, if you want to put the name of the data, we have to put a quote, a single quote or double quote, and I want to do it. So and now we are going to copy the path since we have imported our data. So we copy the path. So I click on copy path, then we load this. So it's going to show us just this way. So we're going to look at it if it's going to load our data. So which it did. It has loaded the data. So and we can just see the data and say data dot add just to view the data. So then we run this. So we have data.add. Then okay, so we have this. This is our data. So now after that we can see this. So and we can just try as much as possible to check some the way our data is. You can say data dot describe. So then we can run this. So now the data dot describe shows the summary statistics of our data. So it shows the count, mean, standard deviation, minimum, the 5% out, 50% out, 75% and the maximum for everything because everything is numerical. So it just does that for that. So and that's just it. So and if we want to see some other things about the data, so you can say, let me do this. Let's have this. You can say data dot core. So now this data dot core, what it's going to do for us is going to find uh, the correlation. Just going to show us the correlation between each of the variables. So now, merely looking at this here, we can see here there's going to be perfect correlation, which is 1.0 between the same feature. So now, if you look across board, you can see the correlation between some features, some certain features here. So this can point us to a lot of things on what we can do. So, but if you look at this, we have between L start and and median value, you can see that the correlation is 0 - 0.721. So, but mind you, note that correlation is not causation. So, what this actually shows a very high positive correlation. So we can see negative correlation rather here as well, and positive correlation here. So these are just to check the way our data looks like, but we are not interested in that. So what we just want to do is just try um, to get to build a linear regression model and check the metrics. So, and to do that, we'll try as much as possible to now pick our features and target variable. So now what's going to be our feature and target variable? Now, if you look at it, what we want to do is predict price. So, and the price is known as the median value. So that's what we're going to do. So, and we are going to try as much as possible to now pick the target variable, which is y. So these are target variable, and the rest of the data is um, that is the feature that we are considering, which is ranging from address cream, SN, indoors, chars, and so on and so forth. So excluding that is MEDV. So we are already selecting our features and target variable. So now we already have this. So this has already run. So now the next thing that we want to do is now use our train test split. So we already imported train test split from SKLN, but model selection. So try as much as possible.
Hello. Sorry
Yes, sir.
for interrupting you. Can you just show the new value for X, new value for Y, so they can see that the med V has been dropped with your code.
Okay. So if I run this, let us. Okay, sorry. Let me copy to X. Okay, and let's try and run this again. So now, if you look at this, yeah, um, merely looking at this, we can see here that we have X as an array, and looking at this value, we have right from 6.3200 up to we have 4.980. So this is just showing us all the whole column that has to do with the first feature here, which is cream. So it's showing us. So and it's showing us again. So if you calculate it, here we have. Let me show us this from our data frame. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 features, which are all of these. So and one target variable. And here, if you look at this, we have this, which is the first one, 1, 2, 3, then up to the 13th one. So it is not showing the last one. So if I want to see the last one, so you can say y, just where we have it here. So y. So we'll try and run this. It's going to give us as an array. So which is this? So which you can see. So we compare the values, showing us everything that is there. So showing us everything. So if we check look at the data frame, the first data point is 24.0, which you can see. 21 point followed by 21.6 at 4.7, and which you can see here as well. 21.6 at 4.7. So, which means that we have successfully picked MEDV, median value, as the target, and we dropped MEDV here and picked the rest of the features as the features that I want to use to train the model. So the next thing that we're going to do is, like I said, train test split. So we'll try as much as possible to just come up and say that is split the data into training and testing sets. We want to split the data into that is training set and testing sets. So, and to do that, the thing there is that we are going to say x underscore train, comma, then I'm going to say x underscore test, comma, then we'll now specify again as well. So we're going to specify for y train and y test. I'm going to say y underscore train and y underscore test. So then we say it is going to be equal to that is train underscore test underscore split. So it's already popped up here. So we just put it here. Then I'll put it in braces as parentheses. So then the next thing is we specify the feature, then followed by the target variable, and we now specify the test size. Say test size, a test size is going to be we'll call it 0.2. So we just want to use 0.2. So we use 80% to train. So then we also specify the random state. Random state is equals to 42. So I already choose that as 42. So we have this. So then we can run this line of code. Then so it has run successfully. Now the next thing that we're going to do is we will try to build the linear regression model. So we want to build the linear regression model. Just build it. So now to build the linear regression model, there's something we have to do. So we have to now call the linear regression model we imported from the first line of code, which is this. Yeah, this. So we are going to assign it to a variable. So we are assigning it to a variable. We are going to say it is going to be LR as linear regression is equal to, now say it's equal to linear regression. So this is it. So I'm put parentheses here. So now by so doing, we already imported it, like turn into a variable, and we'll now use it on the train features and on the train target variable. So we're going to do that. We're going to say that is lr dot fit, because we're trying to fit. So lr dot fit, what do you say, x train and y train, x underscore train comma y underscore trend. So we now run this. So now, since you already run this, so we can see this that it's already has already run. So now the next thing is now to make predictions on the testing set. How to make prediction on the testing set. So say to make prediction on the testing set. So now to do that, we have to say that since we want to do that, we have to now say y predict is equals to lr dot predict x test. That is y underscore predict is going to be equal to lr dot predict as linear regression dot predict based on the what? Based on the x test. So which is this? So x underscore test. So and we are now going to run that line of code. So run this, and it has make the prediction. So if we want to check the prediction, we can actually go ahead and just call the variable, but we won't do that. So, but what we just want to do is just this. We want to plot the true value against the predicted value. So just like I was explaining yesterday. So try and run that. So now we have this graph here. So where we have the predicted values and we have the price, which is the normal value, true and predicted value. So which is this here, whereby we plot say PLT dot scatter y test and then y predict, which is the predicted value using the x test. So and then we said the x label is going to be prices, and while y label is going to be predicted value. So which gives us this plot. So now the other thing that we now need to do is we need to check the metric. So we want to calculate and display the evaluation metric. We want to calculate and then display the evaluation metric. So now to do this, we need to if you remember, we actually imported a metric from the start, which is said from sklearn.metrics. We said import mean squared error and mean absolute error. So we need to assign variables to these two metric. So how can we do that? We now say that I'm going to say mean squared error, which is MSE for short, is going to be equal to that is mean squared error. So then we have it here. So now the mean squared error, which is going to be based on the y test and the y predict, going to be based on the y test and y predict y underscore test and comma y underscore predict. So we have it this way, and then we are going to as well now say that the mean absolute error, which is for short, MAE for short, is going to be equal to the mean absolute error, which is MEAN, mean underscore absolute error, which we have here, and which is also going to be based on our y test and y predict. So we'll copy this and we paste this here. So now, since we already use our mean squared error and the mean absolute error on it, so we are going to print it. So now to do that, I'm going to say print using the print function. I'm going to say use string mean squared error. That is MSE. So as we will do that, then we now also do the same thing. Say print mean absolute error. And as the variable, we said MAE, which we introduced here. So we have it here. Then the next thing to do is just to run this. So by running this, we have this value here. So we have the mean squared error as this and the mean absolute error as this here. So which shows that we are done with the uh, the linear regression model. So the next thing now I'm going to do is I'm going to move to the deep learning aspect. So I don't know if there is any question you can ask your question.
Okay, can you hear me?
Yeah, yes, I can hear you.
Okay, let's say we are just doing this now. We have two metrics of measurement of the error. Um, we see that one is huge, one is small. I understand that so how would you know now? Let's say you're using only the mean square error. How would you tell whether it's high or low?
The only way to tell that it's high or low is to compare it with the deep learning result, and that's what we want to do. So that's why we want to use the deep learning on the same data we used to feed the linear regression algorithm. So it's that result that we compare it with to know if it is high or low. I want to compare the two of them. I hope you get what I'm saying, sir. Okay, sir.
I do.
So okay. So is there any other question? Okay, I think no more question. I think I
Yeah,
can carry
hello.
on. Hello, sir.
Yeah, I just need a little clarification. While you are doing the train test split, that random state, what is
Yes.
the rationale behind using the 42? Is it constant or we can use any other number?
Though it is constant, but you can use any other number. But most of the time, since the time I started doing data science and stuff, I've seen that that's the value that they always use. And when I actually made my little research on why it is that particular value, and which I confirmed myself, and which I explained yesterday, it is to make sure that when it wants to pick, while I say it, when it wants to pick the data for the training and the testing, when it wants to split it, it's not going to just go ahead and, let's say, for example, let me give example of this. Let's say we have 10 people in a room, and or let's say we have 10 people on a queue, and you now say you want to give five people gifts. So now you are not going to, you are not giving randomly. It means you just first give the first five people on the queue. So which means the last five will be unlucky. So do you get that analogy? So now when we now say random state is just like saying, okay, I want to pick randomly, and I want to give this gift randomly. I won't look at, okay, who came first, who came last, or who is the fifth person on the queue. So I just want to pick randomly, and I just issue out the gift. So that's the same rationale that, okay, the the picking of the data points for the training and testing is going to be like, it's going to be shuffled. It's going to be picked randomly across both, across the whole data. It's not going to be that, like for example, we have 506 rows in the data set for the housing Boston data set, Boston housing data set. And if we want to pick the training, we can't just go ahead and pick one to, let's say, one to 350 to use to train, and the rest we use it to test. So no, it won't make sense. So we have to like pick randomly. So it's not like we are picking just uniformly. I hope you get what I'm trying to say, sir.
Yeah, 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 yeah. Sorry.
Okay.
Please, we're having less than 5 minutes for this link to be off. And let me try to add to what the question you have just raised now. When you mentioned that 42, 42 has been the usual figure being used. It can be changed. You can use 32, you can use 30, you can use 40, you can use 70. The major reason why 42 is just there, or that statement is just there, that random, is just that if another person run the same code with your random states, that person will get the same result with you. That's just the meaning of that random state. So if you decide to remove the random state completely and you run that code first time, study the results. Run in second time, the result for second time will be different from the first time because it did not include that random state. The meaning of the random state there is just an example that follows systematic random sampling. You see, when we talk about random sampling in analysis, we have about four. We have stratified, we have simple random sampling, we have stratified random sampling, and systematic. So, under systematic random sampling, systematic means that when you pick the first number, the next number you will pick, probably you are picking the first one on the row, the next one you pick number 7. That means between 1 and 7, there are differences. The difference is 6. That means the next after
Yeah.
7 should be number 13. The next will be number 19. That is the meaning of systematic random sampling. And that follows the same procedure with these random states. What you are saying is that you want system to follow that your procedure. 42. It could be any number. It could be 0. In fact, it could be 1. It could be 10. It could be 100. So that random state can be any number because it's random and can be any number. But most researchers these days use 42, 42, 42. It's not that that number cannot be changed. That number can be changed. It's just to have similar results, the same result. If another person run the same code next time, that's just the meaning of random state. Can you proceed, please?
Okay. So we are going to move to the deep learning part, so which we are going to do now. And okay, so we are going to try and import some certain, I'll put it this way. I'm just trying to do it in the same place, so trying to get the feeling of what we are doing. Let me just put this here. Now we are importing NumPy again, but which normally this is supposed to be in another notebook. So Panda, Matplotlib. Now from Keras itself, we import sequential, we import dense, and we import standard Scala. That's from sklearn processing, and from sklearn model underscore selection train test split again. So we will still talk about this from Keras model, what sequential means, what dense means. So we'll still talk about that. But we want to assume that we already have our data loaded already. So which means that copying this, we are using, so I don't need to import the data again. sorry, to import any data again. So we are trying to use this same data we use, and at the top for the linear regression is what we want to use. So I'll just display the head here just to show us that we already have it here with us. And the next thing I'll try and do is that we'll try to separate features and targets. So which we already did above there, where we have our X and we have our Y as well. So which we have our X here and we have our Y, which is the target variable. So the X for the features and the Y is for the target variable. So which we have here. So the next thing we're going to do is we are going to now normalize the input data. Now, to normalize that, we are using the standard scalar, which is another way to process the data which we have in scikit-learn. So okay, sir. So from where we stopped, I'll continue from there. So like I said, we want to normalize the input data. So and how we're going to do that is this. I'm going to say we want to normalize the input data. So now to do that, we are going to now say that scalar is equal to what to say standard scalar. So it pops up, then we have this dot fit x. So and because you have this now, we're now going to say that x as capital X is going to be equals to scalar dot transform x. So we run this. So already have this run. So which means you have normalized the input data. So now we want to split the data into training and testing set. So I'm going to just copy that and paste it here. I'll just try and do this here. So and the next thing to do is we now want to define our model. So to define the model, this is what we want to do. So we just say define the model. So the model we want to use is a CNN. So and here, if you look at it, we have we imported sequential. So and apart from that, we have a dense neural network. Yes. So and we have the input. The input is the X train, and we use an activation function which is ReLU. And also we also have another dense layer as well again. So where we have dimension is 32. So we have the activation function also is ReLU. and we add another dense layer again, which is one, so which is going to um, specify the output of what we want. So now, if we run the model we define, then the next thing to do is to compile the model. So, and to compile the model, we just say model.compile and say loss is equals to mean squared error, and the optimizer is going to be Adam. So, which we just run this. So, and that's to be able to help us to compile our model. That's for the model compilation. So the next thing to do is after we have compiled the model, we want to train the model and we want to save the history of the model. So, and the reason for saving the history of the model is so that we can plot the training and the validation. So, we want to we want to save it as history. So, but normally, if we don't want to save the history, we just remove this and put model.fit x train y train and say validation underscore split is 0.2. So the number of epochs, batch size, 16 and variables, which I'll still explain what all these means later before the class end. So we are trying to save the trained model, the history, so we can be able to plot the the difference between the training and the validation to see maybe the model really learns the let's say the pattern or really fits on the data and really understand what is inside that data. So that's the essence of trying to save it as history. So now it has started training, you can see. So it's showing us the validation loss, you can see. So it's still training, keeps going, and see. So and it says still waiting. Stone, which is 100 over 100. Since we what we did was this was to set the number of epochs to 100, so that's where it stopped. So and the batch size we set it to be 16. So and which we trained it. It shows us the loss during the training and shows us the validation loss as well. So and apart from that, then we can go ahead to plot the to plot it. But before we plot, we need to first of all evaluate the model on the testing set. We want to see maybe our model actually, let us say, maybe it's performed very well or not. So, and to know that, we want to check the mean squared error, which is on the X test and the Y test, just the way we did for the linear regression. So, and try and do this now. So now we can see the mean squared error here. It is 11.512. And when compared to the mean squared error, they are both here. Mean squared error is 25.01. You can see the difference, the margin is just just too much. So we have 11.5 here. So which shows that the deep learning model is actually better than the linear regression model. So now, in order to actually see that, we want to now show uh, the plotting of the training and the validation loss values. So to do that, we are going to first of all come up this here. The next thing to do is want to Okay, so we'll try and specify the history. Say PLT using matplotlib. So PLT dot plot history dot history and
Hello,
loss.
facilitator.
Yes, sir.
Yeah, well done. Please, why do we have that much range between the deep learning mean square error and the deep learning?
Okay, so
You can see that the first one was
this is the
25
reason why we have
because that difference is just too wide.
is too wide. Yes. So which shows the efficiency of deep learning. That deep learning is far much more better
Okay,
than
better.
machine learning.
Okay, than
Yes,
machine
exactly.
learning. Okay.
Exactly. When it comes to learning patterns in a data, deep learning is much more efficient. So that's why you can see this the gap between the mean squared error of the machine learning and deep learning. So you can see it's very wide. So that's the reason. So is there any other question?
Is it possible if you try Jordan metric, the absolute mean absolute error?
No, we can only use the mean squared error. Yeah, in this case. So because that's what
Okay.
we want to actually see as only the mean squared error.
Hello, please.
Hello, ma.
Please, I didn't get the defining of the model up there. Please, I don't know. The dense and the other things, say you explain it.
Yeah, I will explain. I'm coming. Yes, I will explain it.
Okay, you do that later.
Yes, I'll do that
Hello,
before the
Sam.
end of the class. Yes,
Hello.
Sam.
Yeah. Please, I want to ask why you in the deep learning part you used the X test, Y test to evaluate the model. Why in machine learning you use the Y predict and Y test? Why is that discrepancy?
Now, the reason for that is this is um, when we look at the machine learning aspect, why we use the Y predict, it's like you said here. Let's see that. Yeah, why test and why predict? It is because when it comes to machine learning is a model, and we are trying to compare if our data can actually work on unseen data. Our model can work on unseen data. So, and we are trying to compare the predicted value against the expected value you are supposed to have. So the model itself is there, but the model, we want to know if the model will actually predict the exact thing that we have. So, and merely now feeding, I'm coming, sir. Merely feeding the predicted values, that is feeding the model with the features, and we got some values here. So we want to see maybe they actually correspond together. That's that for machine learning. Now, looking at deep learning, in this case here, while we are using the X test here and the Y test, is that um, the testing set here, we have the X test. Though the deep learning model is just an architecture that actually learns and unravel all the pattern inside the X train and compares it with the Y train, and it wants to see if we actually have okay the same thing. So, and this X test here is the one that we have reserved for testing. You got what I'm trying to say, sir? So
Yeah.
now, the one we reserve for the testing, I will now compare it, we will feed it inside the neural network, which is the architecture, the model architecture itself, and try to compare it with the white test that we have. Because if you remember, when we were trying to split into, let us come back here. So you try and what I'm trying to say. We're trying to do something here. We're saying X train, X test, Y train, and Y test. You got what I'm trying to say, sir? So now what
Yes.
we are trying to do is that we want to compare the X test, which the test value where we will put inside the deep learning itself, since we already have a model, the testing value. So we want to now see that testing value if it is going to give us the same values as the white test. So that's just what that's what that means. But in the other case for machine learning, it is the features that will feed inside the model and get a predicted value. So that predicted value, we want to now compare it with the exact value that we have. So it's just almost the same thing. But in this case here, the y predict that we fed that we are trying to get in this case here is because of the value we will get when we put the x test. It's just still the same thing, just like saying the y predict is still the same thing as the x test. And here in this case, we have the x test here, which is going to be y predict, because we are feeding it with the test variable, which is going to give us the predictions that we have, and we want to compare it with the y test that we already chose to compare it with. I hope you get what I'm trying to say, sir.
Thank you.
Please,
Okay, sir.
please, I want to ask, where did you define the model? Because you're using model.evaluate. So where was the model defined in the first place?
Okay, so well, the model was defined here.
So you're using it here.
Yes, exactly. The model was defined up here. This is it.
Okay,
This is what the
model
model was.
sequential. Okay, I see. I think the reason why the last question, why that last question was, it was a very good one. I think the thing is, I see a lot of inconsistency in this machine learning and data science things. And so, the thing is, like he had rightly identified in the first place. They call they just call y predict and y test. And then
It is the same thing. There is no
no,
inconsistency there.
I,
The thing there
I
is
understand, But what I'm saying is, if there is kind of consistency, one can easily carry over what he does in machine learning to deep learning. Predict now in deep learning is embedded in the object model. That's why you didn't do it exactly the way it's in machine learning. It's not your problem, but I'm just saying some of the observation I'm making. These are just programming things.
okay. Thank you, sir, for that observation. Okay, is there another question? Hello, is there another question?
Fire on.
Okay. So the next thing here is that we said we want to plot the training and the validation loss value. So now this is it. We have the training and we have the validation. So we have the loss. Now, ideally, when it comes to deep learning, training deep learning models, this is the ideal way the training should go and the validation. It should always come down like this. But in the case where it goes, maybe let's say it comes from here, let's say start from here and start moving up and the loss keeps going up, that means that there's something wrong. So it means the model itself is not actually getting to understand the pattern in
Sorry,
the data.
what is
So
on the x-axis? We are not seeing what is on the x-axis.
what's on the x-axis is the epoch, and what the epoch is talking about is it has to do with let me put it this way so you can really get what it means. So in deep learning, an epoch refers to a one complete pass through the entire training data set. So it's just like when we say one complete pass, meaning that the number of times the model itself or the architecture should go through the data in order to understand it. Let me put it this way. It's just like this. let us say when we were growing up, there are some places we can't just, for the first time when we go there, we don't really understand, okay, the direction of the place. But as we go there over and over again, we just understand the terrain, and we get to know, okay, this is this place, this is this place. That's what epoch is about. It's just like trying to say that, okay, if I'm staying in Ikeja and I want to come to, let me say, Unilag. So there's a route that we actually pass. So that epoch refers to like the number of times I should go to Unilag for me to be able to understand the route to Unilag. So do you get what I'm trying to say? So, and during an epoch, the model's weights are always updated. So when the weight itself, when we talk about weight, weight means the importance that is given to a particular feature. So the importance that is being given. So the more it actually works through over and over again, then it keeps updating the weight. It updates the weight. The more it goes through, so in batches, it keeps doing that and it keeps doing that. So before it now finally be able to generalize very well on the data itself. So and that actually has to do with the batch size. So and the batch size actually has to do with the training data, which whereby is divided into smaller subsets so that the model itself can actually go in batches. So it goes in batch that, okay, go through this batch, learn what is there, go through this batch again, learn what is there, and keep updating the parameters like the weights and the biases, and keep doing that, keep doing that. So that's just what that is about. So, and I hope I've answered your question, sir.
Yeah.
Okay. So, and as pertaining to this graph here, so the loss, which has to do with the y-axis, as you are seeing it, yeah, and the epoch, which is on the x-axis, which as you are seeing here. So the loss, which is on the y-axis, it actually represents the loss of the model. So, and which is a measure of how well the model's prediction matches the actual data. So, and in this case, it appears to be using the mean squared error as the loss function, just the way we have specified it there. So, and for the x-axis where we have the epoch, so and it has to do with which one complete pass through the entire training data set, the number of times um, it goes through a complete pass, and that has to do with it first go through it. Okay, after it has gone through the number of times it goes through the data set, 20 times, 40 times, 60 times, 80 times, and 100 times. So how well has it generalized? So before it's between 0 to 10, yeah, you can see that it's already stabilizing, trying to tell us that, okay, at that 10, the number of epochs, when it has gone through the data set 10 times, it has actually been able to generalize and understand the pattern. So, and then when it now gets to 20, 40, 60, it was able to now say, okay, yes, I can generalize very well. I already understand the data very well. And that has to do with that the loss has to keep reducing up to closer to zero for us to be able to say, yes, it has been able to generalize very well. I hope you get what I'm trying to say. I hope we get it. So after it has gone through the old data set in batches for 10 times, so it was able to generalize very well that, okay, yes, this data, I already understand the pattern, I get what is there. And that's what actually made us have a mean squared error of 11.5, and which is actually very lesser compared to the one of the machine learning algorithm. I hope you get it, sir. So, and with that,
Yeah, please. That's fine. Please, sorry. Whenever you're showing a graph, make sure we see the entire graph so that we can always make sense of it. Because so that you're always having a small thing that you need to use, like open setting, blah blah blah, under
so that you can close those so that we can see well. Thank you. It's fine. Mhm.
Can you enlarge the graph or can you just click on the graph to full screen?
It's fine the way it is. It's fine now.
Okay. Okay. Dr. Adejo George, you have a question, please?
Yes, good evening, doctor, and good evening, presenter, and to everyone. Please, I have some very basic question on deep learning. You know, when we did our machine learning class, one of the things that we were taught was that it applies to two sides, whether you're dealing with a problem that is regressional or you're dealing with a problem that is that can be classified in terms of classification. And we studied different models and algorithms on these two sides. And then we also dealt with the practicality of these models on different situations, their best application to different problems. You know, so, and in terms of this deep learning, I don't know if you can help us so that for someone like me, I'd love to understand that part so that when I'm working on my own and I have a data set, I know I know exactly how to navigate my way. And then how do we relate it to convolutional neural networks or the RNN and so on and so forth. So I think that part will help me to be able to follow the class very well. Thank you.
Okay, sir. As regarding your question, we have not gotten into deep learning actually. So in the next class, we are going to be talking about each architecture. We are going to look at CNN. We are going to look at RNN and so on and so forth like that. So, but we are just trying to show comparison between machine learning and deep learning now. So, but basically, deep learning is used most especially for computer vision projects. Yes, so to train computer vision projects like object recognition, character recognition, face recognition, and basically images to train images. So, and we just try to use a data set just to be able to show us how well deep learning is useful when it comes to unraveling pattern and learning the pattern in a data set. So when compared to machine learning algorithm. So that's just what we are trying to do. So, but we have not gotten into it. So when we get there, we will understand when I start explaining all these things. We are going to break the architecture very well. Basically, we are focusing on recurrent neural network and convolutional neural network. Those two, we are going to explain it very well because they use it most of the time for research when it comes to deep learning projects and computer vision projects. I hope you get that, sir.
Yes, very well. Thank you.
Okay, sir. So, do we have any other question?
I don't think so.
Okay. So, this is all for what we are trying to do. So I just tried to show us um, the difference that we can get between the machine learning task and deep learning task when we use the same data set. And by saying that, we can see that from the mean squared error, which is actually the metric that we use to compare the two algorithms, which is the deep learning and the machine learning, where we have the mean squared error for the deep learning is 11.5 to one decimal place, and the one for the machine learning is 25.0 to one decimal place. So, which is just basically times two. So, and on that note, so we end the class here. So, and I would like to look at our assignments. For most of us that have not done the assignment, so I would like us to do the assignment and submit so we can go through it and comment. So basically, I want us to publish a paper. So that is you yourself, you're going to publish it. So just convey an idea what you have been, be dying to work on using deep learning, or even if it is machine learning, you can actually consider that. But we will actually appreciate if it is deep learning, basically, which is training images either in health sector, either in transportation sector, maybe plate number recognition or anything, so you can lay hands on data. So just want to like make this class that you just learn, but you should be able to practice and implement. So that's just the main idea. So with that, on that note, thank you very much. So this notebook, we are going to share it. So I'll download and send it now.
Hello, excuse me, sir. You said you're going to explain the lines of code to us.
Okay, which parts are?
Deep learning.
Okay, so I'm coming. Let me just
Right.
try and
You
download
said
it.
about the dense to dense.
Okay, I'm coming. Just want to download this first. So, okay, good. So I want to try and I'm coming. I want to try and send the notebook I just finished with now to the group chat so we can.
We can put that after this class because our time is very important also. So please try to explain so that we can have a comprehensive recording session, please. The time is fast
Okay,
approaching.
sir. So
Zoom it out. Zoom the codes out.
yeah, we'll try and zoom. Okay, I'm coming. Think it's clear enough this way.
Yes. Yes. It's clear in that way. Define the model. But can't you go up a little bit?
Okay,
What about 21?
this way.
Aha. I think okay. 20. Okay, yes. I think you can okay, that way.
Okay, so now when we talk about defining model, basically in deep learning, for you to be able to define your model, there are ways to define the model, and we have to actually import most of the things that we are going to need. Now, there are different layers and different, let me say, connections when it comes to deep learning. So deep learning is not just a standalone. You have to specify the things you want in in your model. So for example, now when we consider CNN, which is convolutional neural network, we have a simple CNN. So that simple CNN is just very simple, so nothing more or less. And we have other ones like faster, um, that's recurrent convolutional neural network. We have faster recurrent convolutional neural network, so we can be appending a lot of things to it. So now when we talk about that sequential, now sequential is just trying to tell us about let's say when we want to, just like when we want to build a simple conveyor belt. You get what I'm trying to say? So each step on the belt, we have to process some information. So the sequential model means things will be processed in the order you set them up. So one step after another. You get what I'm trying to say now? So that's what that actually means. That's for the sequential. So it's just like the driving force on whatever you have defined in the model. That's what will make it flow in that order and work hand in hand together. So now when we now talk about the model.add dense 64, we will now say input dimension is equals to x underscore train dot shape and activation function is ReLU. So it's just like, let us imagine this as adding a processing station on our conveyor belt, still using the conveyor belt terminology. So, and this station has, let's assume that it has 64 workers, which means neurons in this case. Now, just like we have a station, so they have a processing station that have 64 workers. In this case, is the neurons. So we are all going to work on understanding the data that is coming inside. So the data that is coming inside, so that's what the model.add dense, that's, let's say, input dimension is equals to x underscore train dot shape. So that 64 neurons are the ones that are going to be trying to get to work on understanding the data that is coming in. So, and the input underscore dimension is equals to x train dot shape. The part, that part tells us how many types of information or features each of the neurons needs to consider. And then the ReLU, which is the activation function, is a type of instruction on how they should process the information in a way that they ignore negative values and only pass on positive values. And in the case of um, a segment function, if you look at it, it will never return a negative value. You get what I'm trying to say? Just the way we see in the last, I think, 2 classes before then, where we talked about activation function, where we did calculation using the ReLU function, which is 1 over 1 plus e raised to the power of minus x, where we put a negative value and still give us positive value between 0 and 1. So that's what that part does. So now, in the case of the model.add dense 32, activation ReLU, and now this is another station again, just like another layer, well, with 32 neurons, and they take whatever the previous layer, which is the 64 layer, has figured out, and they try to make more sense of it. So, and they also use the same activation function instruction to process the information that is being recovered from the layer, the 64, where we have the 64 neuron, where the information is being passed into it, and they try to understand what is going on there and actually send it to the 32 neurons, that is the one that is after the 64 neurons. So, and the model.add dense 1, this is just like the last station, and it just has it's just like a one worker whose job is just to summarize everything that is been learned by the previous layers by layers by layers. So we can keep adding more layers. If we want to add more layers, we can add. So, but in the end, we just have the last one, which is the one. So, and that one actually help us summarize everything that has been learned into one final score or prediction. So it is that last neuron that is going to actually give us the output, just the way we explained when we have the output for when we talk about the what do we call it? Then we'll talk about the whole function where we have the y as the output. So that one is the output here. The model.add dense is the output. I hope we get what I'm trying to say. So that's just the simple explanation for that.
Hello, excuse me, sir. In
Yes,
that model, can you hear me?
yes, sir. I can hear you, sir.
Yeah, yeah. After the line that has the sequential,
Yes,
the
sir.
next line where we have dense 64.
Yes, sir.
Now there is one in square bracket there. What does it mean? That one in square bracket.
Okay, this one in the square
Yeah, in
bracket.
square bracket. Yes. What does it mean?
Now, this square bracket. Okay. So now, since we have, let me try and look at this.
Yeah, that one is square bracket. That's x train dot shape, square bracket one.
Okay, come in, please.
It is a member of column feature. Column feature. the number of columns feature in the training data set S train. That's what it means. We're talking about the column.
Exactly.
That's what it means.
All right, sir.
Okay. When we talk about the that line itself, that model.add. Sorry, I'm half kata, so I have to do that way. So when you have model.add, it's a method that had a layer to the model. That model.add itself. And the density 4, that's a layer being added, specifically a dense, fully connected layer with 64 neurons. That's what it means for that density 4. And then you have the inputs, input underscore dim. There's got to S train, the shape 1. This specifies the number of input features for the layer. So in this case, it is said to be a number of columns, the number of columns in that training data set, for that S train. Then you have the activation. Activation is called to ReLU. So this specifies the activation function for the layer, which is the rectified linear units. That is a ReLU. The ReLU there is written in that small letter. But what you write in the center, it will be capital R, then small e, then capital L, capital U function. How you get it the way I explained that now?
Sir, thank you, sir.
All right. So any other question, please? Our time is almost up. It's about 10 o'clock. And I promise some people that will not exceed 10 because of their time difference. Some of us are here in other countries, so not Nigeria. Our 10 here is like 12 a.m. in another country where they are. So please. Okay. David Kende is raising hands. Can we hear from you?
All right. Yeah, thank you, sir. I want to ask, what of in a situation that we want to have more than one output? Let's take, for instance, that let's say we have many inputs, but for our targeted value, we want, let's say, 4 outputs. How do we handle that?
When we get about that, we will see that when we get to training a computer vision project, whereby we want to be able to detect if something is faulty, not faulty, broken or not. So those are the outputs. So like you said, 4 outputs. So when we get to that part, we will actually look at that. So this is just because we are looking at one feature, which is the price, which is the output here in this case, which is the model.add dense one, which is going to be just the single output. So in the case whereby we're going to have 2 outputs, we put dense 2 here. So dense, if it's 3, we put 3. So depending on the target variable that we are actually looking at. So that's just the thing that is there. So, but we won't appreciate this better with this type of data, but with a data where we have features like, let me put it this way. For example, when we are working in a factory where we have materials that are faulty, whether it has crack or it broke or it is okay. So those 3 things that are like that, they are features that we might want to predict at the end of the day. So which means that we have 3 things we want to actually predict. So those are 3 outputs on their own. So I hope you get it, sir.
Yes, I get it. Thank you, sir.
Okay, sir.
So when there's no question on these notes, I would like to declare the training ended. We appreciate your patience to this moment. Thank you very much, and God bless you all.